we will uh, do the problem that is requested by Manjuender. Basically, the last problems of the contest related to this video. So if you also have a request for me to explain something, just put it in comment, and once I got the time to do this, I will do it. Usually I have the time during weekend, but sometimes if my work actually require me to work on weekend, so I cannot do it. But just put it in. Once you put once a time, if I can do it, I will do it. So now let's go into the problem exactly. The problem is this problem. 2, 3, 12 selling pieces of wood. The difficulty is hard. So if you are actually what you call that um, doing this for interview purpose, usually they won't ask you the hard question. But if you do want to watch this because you want to what you call it curious about it and want to solve it, let's go into it. First of all, let me refresh this one first. Okay, let's do about start from the problem. The problem is that we have a block of wood with the size of m times n. M is the height, n is the width. And we also have this price list that a wood with a certain height and a certain width can be sold with a certain price. But you cannot interchange the height and width to get the same price. Okay, the reason is because the grain of the wood makes a difference, so you cannot rotate the piece of wood. What it means is, for example, if we have a 2 times 1 2 times 1 wood, height width of 2, 1 is the width. This is not the same price with 1 times 2. Okay, that's what it means. So given this size of wood and this price list, the question is what is the maximum money that we can get? Okay, and the restriction just now is you cannot rotate it to mean to sell it for the same price. So the rotated one, if there is a price to sell it, it will be a different price in the price list. Okay, so for the constraint, let's see the constraint. All shapes of wood are pairwise distinct. That's where it guarantees, meaning that the same dimension will only have one entry in the price list. And let's see the example. In this example, we have 3 times 5, 3 times 5, and this price list. And then the solution is 19. 19, we got it from cutting 2 times 2, which has the price 7 twice, so total 14. And we also cut a 2 times 1, which has the price 3. And we also cut the 1 times 4 with the price 2. So 14 plus 3 is 17, plus 2 is 19. That's it. That's the problem. Now, how do we solve this? The essence to solve this is basically to build on top of what has been calculated before, which is a dynamic programming. And how to phrase this? Let's take this as an examples, okay, to bring about the tactics. So let's start. We need oh, we need 5 of it. Basically, this is to represent the block of wood. And how do we do this? Basically, we look per cells, and then if you notice, for example, if we go explore it like this, just take the horizontal first, okay? Basically, if you notice, this wood, the 1 times 5, can be built with a 1 times 5, or it can also build with a 1 times 4 plus 1 times 1, right? And the 1 times 1 is equivalent with anything has been built with the 1 times 1 before. So that's what it means by trying to check from what we've calculated before to find the maximum money we can get when we are exploring a certain rectangular, sub-rectangular of the wood. Let's try to run this from several runs of this to make it more clear. So let's try from the first one, 1 times 1. 1 times 1, is there anything we can sell with a 1 times 1? Nothing, right? So 0, that's it. Is there anything before it? Nothing also. So that's it. 0 is it is. How about now 1 times 2? Is there anything we can sell with 1 times 2? Nothing. Is there anything we can sell if we build from something less of the sub of 1 times 2? What is the sub of 1 times 2? That will be 2, 1 times 1. But we know that 1 times 1 was 0. So even if we try to build from 1 times 1, we sell it for 0 in total. So in total, it's still 0 here. How about 1 times 3? Is there anything here for 1 times 3? Still no. Is there anything from previous one? Still no. Everything was 0 if you remember what we calculate. Okay. Then now goes to the 1 times 4. Is there anything for 1 times 4? Yes, it is. We can sell it for the price of 2 with 1 times 4 block. Is there anything we can build with things before it? Nothing, because it was all 0 before, right? So even though we can build it, but we cannot sell it for anything more than 0, anything more than 2. So 2 is the highest price for 1 times 4. How about 1 times 5? Is there anything in the 1 times 5 here? Nothing. How about the thing before? Yes, there is. We have 1 times 4 plus 1 that will in total having the price of 2. 2 plus 0 is 2. So 1 times 4 plus 1 times 1 block will build the 1 times 5 block. And it has the price more than 0, which is 2. And the 2 comes from the 1 times 4. Okay? So that's how we build it. We build from what was before. So that's basically the idea of doing it. Let's do some more to bring in the point of the dimension. Just now we always look only on the horizontal. How about we now start to look at the vertical contribution? So let's go with this next as the next things, right? So this may represent a 2 times 1 block, this one. 2 times 1, is there anything for 2 times 1? Yes, it is. 3. Cool. So 2 times 1 also can be built from 2, 1 times 1. But the 1 times 1 was 0. So 0 plus 0 is 0. And it's not greater than 3. So we keep 3 as the maximum price we can sell if we have a 2 times 1 block. Now let's go next. This one is a 2 times 2 block. 2 times 2 block. Is there anything 2 times 2? Yes, 7. Okay, 7 so far. Is there anything we can build from the before? One way we can build a 2 times 2 is from 1 times 2. 2, 1 times 2 block. 2, so 2 of this. But 2 of this was 0, right? The value was 0. 0 plus 0 is 0. So 0 is not greater than 7. We keep the 7. Is there another way to build a 2 times 2? Yes, it is. If we took the vertical block, the 2 times 1, okay? If we took the 2 times 1 and we took 2 of it, we can build the 2 times 2. And the 2 times 1 can be sold with the price of 3. And 2 pieces of this is 3 plus 3, 6. Okay, we can sell it for 6, but 6 is not greater than 7. So we keep the value of 7 as the maximum of it. And so we go on about it. So to summarize the process, we build on the what we calculated before. So we build it step by step per cell here. Up to the cell, at the end of the cell, we have the m times n, the equation. And we can return the value we calculated up to this point as the final value. And to do the consideration of what we built before, we need to see two dimensions, the vertical part and the horizontal part. When we look at vertical, what are the subcomponents, subrectangular for the vertical? What are the subrectangular for the horizontal? Then we compare and we get the maximum, and that's it. Okay? So that's basically the tactic, and this is called dynamic programming because it's built on top of what was before. Let's start the code implementation. To do this code implementation, from the explanation of tactics, obviously we need to hold some kind of two-dimensional array. Let's call this matrix. Okay, and this matrix, let's start everything with 0 values. So m is the height and n is the width. So what we do here, we do this. Why do I do +1 here? This is nor one of the technique to avoid doing if else on the edge cases. So if you notice here, just now the way we check it, we built from what was before, but what happened in the zeroth case? That was nothing before, so you have to handle it with if else. But if you add one more thing here to cater for the zeroth, then you don't need it. You don't need the if else because the previous one was nothing, right? No prices. So it's equivalent by adding just one block to avoid writing too many if else and make our code more succinct. Okay? And then let's do it. Remember what was how we calculate it before was to actually take from initialize it from if there is already a price list with the exact size. Okay? So in this case, height with price in prices. Why I do this? Because this one is not in directly accessible things, right? That's why it's better we process it in separate way first so that we don't do too many looping. Matrix HW is price. And then this is where we try to build from what was before, which is the OE first. The I will be about the M, and then the J is about the N. Okay, so this is basically building from there to there. And then for each of these, we need to look at the two dimension, the vertical and the horizontal. Let's start from the horizontal first. Horizontal means it is looking at the N. N means it's looking at the J. So we start from 1 to J. Why 1? Remember, the additional thing was to avoid if else. So actually we don't really need to calculate the zeroth index. And for each of these J subcomponent, the horizontal one, what we do is matrix IJ, we compare it, whether there is anything that can build bigger than what it was before. So the max from itself compared to what can be built from the subcomponent, which is this one is about J, so we do this. J minus K. Remember just now, the 5 can be built from the 4 plus 1. And the 1 here is the same with this one. That's why J minus K. Okay? And then we do the same thing for the other dimension. It means if we already calculated J, this is about the I. When it's about the I, the J is kept in constant. And the I will be the one playing around with the k. Okay, now once this is all said and done, if we already calculate to the n, the n is the answer. Remember, we have +1, that's why we can access the m and n directly as the answer. One thing here, if you notice, we don't really need to go from 1 to j or 1 to I, but we only need to go to halfway into it because it's just a repeat, right? 1 plus 4 is the same with 4 plus 1. That's why here we can save some numbers by dividing it by 2. Double slash here, making it into an integer result of the division. And let's plus it with 1 to be safe. So we don't miss the thing, the 1 of it. So we just get it over by 1. And that's about it. Let's try. Looks correct. Let's see if it is performant enough. It's accepted. That's it. Now finally about the time complexity. The time complexity for this one is just big OM. This one is just, well, this is just a list of price. And what is a list of price? Can be many. The list of prices here can be many. What do we call this? Let's call this M and O. Let's call this O, big O, O. Okay, big OP. And then this one will be big O, M and is 200. Prices that line can be many. And this one can be, what is this? M plus 1. So at least this one is big O, M. This one is big O, N. So this one at least big O, M times N because this is inner loop of this one. How about this one? So this one is big O. So if you notice, this one is an incremental values of it, right? If you remember series 1, 2, 3, 4, this is actually big O n squared. Because in mathematics, this is the same as n times n plus 1 divided by 2. So if we took it that way, of course there is a divide by 2 here, but in terms of big O, that doesn't really matter. So you can consider here as actually big O n squared. Of course, this is actually between n or m, right? Because it is about I or j. So you can, if you want to be more accurate, it is maximum between m and n. So in such case, we also need to update this one into this. Okay. So now out of this, of course, this is doesn't really matter because this one is much bigger. This could be matter. So what happened here? But of course, even this is matters. The amount of prices possible couldn't be larger than m times. Couldn't be larger than what is actually the numbers of cells in it. Well, it could be not. It couldn't be because it should be distinct. Distinct. It means for a distinct thing to build the what you call it to build the square. It and the amount of the price list will be the at most the same one with the not really. Actually, you can make it a lot. Well, okay. So the time complexity of this will be the maximum either from the price list or this. So it's about you can say that it's about m to the power of 3. That says you notice that the prices will input it into the matrix. So the prices list itself couldn't be larger than the number of cells m times n, right? That's logically it. So we don't really need this because we know p will always be less than this. So this will be the final big O analysis. So it's about n to the power of 3 in generic. But to be exact, it's what you can express it. So that's about it. Thank you for watching.